Hello everyone, my name is Toufik Mohamed Ailane, and today I will be your presenter to present our published work under the name How to Extend the Abstraction Refinement Model for Systems with Emergent Behavior. This work was authored by the speaker Toufik Mohamed Ailane and Dr. Christoph Knieke, Professor Andreas Rausch, here at the Institute of Software and Systems Engineering at University of Technology of Clausthal. So our agenda, I will go through the abstraction refinement model and explain it a little bit, and then I try to provide our main contribution, namely the extended abstraction refinement model, and I will speak briefly about our future work. So at the beginning, what we have here is a waterfall software development lifecycle. So the software development process usually contains various models described with different notations based on many viewpoints and aspects, logical viewpoint, functional viewpoint, and so on. Our approach so far that we have been working on is based on this development model, waterfall development model. However, uh, it the findings in this paper can be applied to a different development model, for example, a V model or so on and so on. So based in the waterfall model, we can tell that by, by based on some phases completion, we recognize a new model that represents the system from a specific aspect. So basically at the analysis part, we recognize a requirement model. By the end of the design phase, we recognize a design model. By the end of the implementation phase, we recognize the implementation model. There can be more models, but we focus on those models as we focus on, on the we try to dedicate our work specifically to understand what is an emergent behavior. So we took enough with these models. However, the model can be uh, can generate more models. So to do this, we start with a formal foundation. So we start with a set of representations, and we define it as M. M represents the universe of all models. So basically design models, implementation models, let M be the universe of all models. And now to relate those models to the software development process, we say that we can distinguish models with respect to their corresponding software development phase. And for instance, in case of the waterfall model that we have chosen, we recognize the following disjoint subsets. So requirement models is the universe of all requirement models such that requirement models are included or equal in the universe of all models. The design DM stands for universe of all design models that are included also or equal in the universe of models. And similarly, the implementation models, the universe of implementation models, EM, that can be included or equal in the universe of models. Similarly, as we define the representations, we say we can define the interpretations as the following. So BT is the universe of all observable behavior traces. And the power set of BT, PBT, is the universe of all behaviors, all observable behaviors. So basically, we focus only on what we observe. And again, because we are driven to define what is an emergent behavior, which is something that we observe eventually. So now that we have distinguished between representations and interpretations, representations are the models that can be in the form of any representation or notation, and the interpretations are the behavior traces. What we do now, or what we need now, is the semantic function. So a semantic function ZEM is a mapping function that maps each representation in the set of models to an interpretation in the set of behaviors. So basically, Zen by definition, it takes a model and it gives back an interpretation from the universe of observable behaviors. So if we relate to our waterfall development model, we can say that we can apply the ZEM function in the following way. So ZEM of a requirement model of a system S. So for a given system S, for system S, which is an element of the universe of all requirement models, the semantic function gives the interpretation in terms of the requirement behavior traces of a system S, which is an element of the power set of the universe of observable behaviors. Similarly, the ZEM of the design model of a system S which is also an element of the universe of all designed models, is an interpretation. The Zem function gives an interpretation in terms of design behavior traces of a system S, which are seen as an element of the universe of all observable behaviors. Similarly, at the implementation model EMS, the implementation model of a system S, its semantics, its interpretation is the interpretation behavior traces of a system S. So basically, the idea of the development processes, such as the waterfall model that we have here, is that the observable behavior traces or the observable behavior of a system S, which we can which we can notate it with OBTS to stand for observable behavior traces of a system S, is a subset of IBTS, of the implementation behavior traces. So basically, the idea is that what we observe at runtime after we develop the model based on the different development phases, what we observe is a subset or equal to all what we have implemented, and not an extra behavior beyond these descriptions or these representations. One important aspect before we move on to the abstraction refinement model is the evolution process or the evolution function. So an evolution consists of the transformation or the change process of the system specification during the different development phases. So basically at each phase, the specification of the system evolves and the new model or new description that defines the system characteristics is developed. This change or this transformation, it can be formalized as the following. So evolve function, by definition, it takes a model and it gives back a model. For the evolution, we recognize four types, namely the abstraction, which is, as the name indicates, that the newly developed model contains all the semantics of the previous model and may contain more semantics. So the model is an abstraction of the newly generated model. And and so mathematically, the semantics of a model M is included. The behavior traces of a model M are included or equal in the behavior traces of the newly generated or the evolved model. Similarly, the refinement, an evolution is said to be of type refinement if the semantics of the newly evolved model are all included in the semantics of the previous model. So basically, we develop a new model in the new phase, which is based on the previous model. However, the semantics or the behavior traces of this model are all included or equal in in the, in the previous model that we used to develop this model. Also, we recognize an evolution of type total change. So as the name indicates, it means that the newly evolved model has totally changed from the previous model that we have used. So the intersection between both behavior traces is an empty set. And then we have a strict evolution, which is an evolution, that that is that the newly evolved model still shares some specifications, some behavior traces. It's not a total change, it's not a refinement, it's not an abstraction, but there are some intersections. So the intersection between both is not an empty set. However, none of them is included or equal in the previous one. And this is what we call a strict evolution. However, for the abstraction refinement model, uh, it's based all on the refinement constraints. So if the condition holds that the semantics of the newly evolved model is included or equal in the semantics of the previous model, then if we refine at each step, then this is an abstraction refinement model evolution process. So if we apply it on our waterfall model that we have chosen, as we said, at the analysis, we get a requirement model. If we respect this constraint and we give a design model, that is that the semantics of this design model are all included or equal in the semantics of the requirement model. And if we continue so with the next development phases, so namely the implementation here, if we check for refinement and the semantics of the implementation model is included or equal in the semantics of the design model, then what the abstraction refinement model actually does is it gives the guarantee that what we will see at the end is we will not see an extra behavior. We will not see something that we did not consider during development. And this is the nice property that comes with the abstraction refinement model. That what we will observe at the end is a refinement. It's exactly what we have seen. It's always included or equal in the previous one. So as we mentioned before, the observed behavior traces that we will see at runtime, they are nothing more than a refinement of what we have implemented here, which is in return a refinement of what we have designed, which is in return a refinement of the requirement model. So basically, this is the foundations and fundamentals that we have used from the literature. And we put the references here for the reader and the listener to go back if they are interested in more details. But the main question that based on which this work has been developed is, where is the room for emergence? Where is emergent behavior in this development process? How does an emergent behavior reflect to each development phase? Is it something in the requirements, in the design, in the implementation? How does it emerge in the first place? How does it evolve with the system? When is it the source of it? When is it generated? So this is the approach that we have chosen to define an emergent behavior. We said that we go step by step, and as the behavior of the software is evolving or of the system is evolving, we try to check how does the emergent behavior relate. So at the beginning, we say that the emergent behavior is a behavior which is included in the behavior that can be observed at runtime. So basically, the emergent behavior is something that we can see, that we can observe at runtime. And hence, we can say that the emergent behavior traces are included or equal in the universe of all observable behaviors, and that the emergent behavior traces of system S is included or equal in the universe of all emergent behavior traces. And again, we raise the question, what does this mean to the development process? So at a requirement level, at the analysis level, we can think of the emergent behavior traces as something that has to do with the requirement behavior traces. So the semantics of the requirement model of a system S do intersect with the emergent behavior traces. However, none of them is a refinement for the other one. So in other words, there is an inconsistency between what we observe, the observed behavior, and the required behavior, what we require. Somehow they relate. It's not coming from nothing. It's coming from there, but they are not a refinement. There is an inconsistency between both. We require something and we observe something else. And this is how it can relate to the requirement model. And similarly at the design model, so we can assume that the emergent behavior traces are included or equal in the semantics of the requirement model. So basically it's there. We require an emergent behavior to take place. We want an emergent behavior to take place. This is part of our requirement. However, it's not a refinement of our design, nor our design is a refinement of the emergent behavior. The inconsistency is happening at the design level. So basically, the emergent behavior is a refinement of the required behavior, but not the design behavior. There is an inconsistency. Or we take it one step further and we say, okay, could it be the case that the emergent behavior is a refinement of the design behavior? However, the inconsistency can take place with the emergent with the implementation model. So with what we have implemented. This makes sense only if the implementation model is not only the code, but also a hardware and so on. And if it is purely the code, then it would make no sense. Usually, if the implementation model is only code, then we will observe always what we have implemented and nothing more. And for the next steps, we will assume that the implementation model is purely the code, and hence the emergent behavior is consistent with the implementation. It's not consistent with the design and the requirement. So to summarize, here comes the room for emergence behavior. So based on a real world observation, we say that we see an emergent behavior that is a refinement of the observed behavior traces. It means we observe it, which is a refinement of the implementation behavior traces. However, due to refinement constraints, the development approach is the following: that we are observing something, emergent behavior traces, that are not included or equal in the implementation behavior traces. And this is a contradiction if we try to define the emergent behavior based on the refinement, abstraction refinement model. And this contradiction is coming from the assumption that the development models represent a complete description of the system behavior. And again, if we want to define an emergent behavior based on the abstraction refinement model, then the idea is to weaken this assumption. And this is what we did by saying that the observed behavior traces are included or equal not only in the required behavior traces, as said by the abstraction refinement model, but furthermore with the unspecified observable behavior, something that is unspecified and at the end we observe. So basically, the emergent behavior traces is part of this unspecified observed behavior. So what we say now is that the emergent behavior is part of the observed behavior but must not be included in the required behavior, for example. And hence we define the emergent behavior as the behavior that is not specified during development but appears or observed at runtime. So to illustrate this or to further explain this, we can see, for example, representations in the form of automata. An automata can be one nice example of a representation of a model, and the interpretation can be seen as the execution traces, those behavior traces of this automata. And as we said, at each development phase, we recognize a model. So for the requirement model, for the design model, for the implementation model, there is always this representation. For the sake of simplicity, let's assume that we can do this in the form of automata at each phase. And then refinement consists of refining in the meaning that the newly generated behavior traces are always included or equal in the previous one. This is just to guarantee that at the end, what we will observe is always what we have specified during previous development phases. However, what we are saying is that the emergent behavior consists of a specification that is more than the refinement itself. This is what we show in the representation here, and this is what we show here, these new sets. And for this reason, we extend the abstraction refinement model to include the notion of unspecified behavior traces. So basically, we recognize the unspecified behavior traces of a system S that are not specified in the requirement model. However, it is included in the design model. And this can be due to design principles, to design constraints, to the skills of the design team. It can be by mistake, or it can be something that is needed by the design. And similarly, at the implementation level, it can include some unspecified behavior traces that were not specified in the design model but included in the implementation model due to, for example, the platform that we have chosen for implementation, or due to the programming language or the skills of the implementation team, and so on. And what we say at the end, that these unspecified behavior traces, whenever they manifest at runtime, whenever we see them, these are what we could call an emergent behavior. So basically, the emergent behavior is the unspecified behavior that we did not specify previously and it emerged. So at the end, the way we want to continue our work, now that we have a clear and formal definition of the notion of emergent behavior as a consistent extension of the existing formal software engineering approaches, we are interested in using DevOps paradigm into this. We think that DevOps really can make use of this. We can make use of DevOps to make use of these findings. So basically what we can do, we can map phases such as requirement analysis, design, and implementation into the dev part of the DevOps paradigm. However, what we do not have is a concrete formal foundation of the ops side. And the idea, so basically we just have an emergent behavior. We are monitoring and we see an emergent behavior. There is no formal foundation in this. The question that we raise, how much formal things can be, so we can develop systematic or automatic solutions. For example, one idea that we are currently investigating and preparing for publication as a next step is the specification mining. Specification mining techniques has been they got developed during the previous years, and we believe that they can be efficiently used to formalize the behavior that we are seeing, the emergent behavior. They can bring this formality, this formalisms that we need at the upside. This at the end should enable us to continuously complete the specification that were developed and we missed that specifying, especially that we are making model-based development, and this should at the end improve the quality of the developed system. So basically that was a 20 minutes trying to describe what we have done so far and what we are planning to do. We would welcome any comments through the emails that are on the paper or any questions. Please feel free to reach out and ask. Thank you very much and goodbye.